So here I have a problem from the 2013 Putnam exam, and it says for positive integers n, let the numbers denoted by this function c of n be determined by the following rules. Okay, so c of 1 is equal to 1, c of 2n is equal to c of n, and c of 2n plus 1 is equal to c of n times negative 1 raised to the n power, where n can be any positive integer. So since it is the 2013 exam, naturally we're going to take the sum from n equals 1 to 2013 of c of n times c of n plus 2. Okay, well the first thing to notice about this is that 2n is kind of math language for any even number. Okay, this is because if you take any positive integer and you double it, you automatically get an even number. That's what it means to be an even number. That means you're essentially a multiple of 2. And since they alternate parity, that means if you take an even number and add 1, you automatically get an odd number. So 2n plus 1 is an odd number. Okay, so before we can even kind of come up with this, it's helpful to plug in a couple of random numbers just to make sure we understand what this function is saying. So today is the 15th, going on the 16th, so we'll just plug in some of those values. Okay, so c of 15, well 15 is an odd number, which means it could be written in the form 2n plus 1. Okay, so this can actually be written in the form 2 times 7 plus 1. Okay, and according to our little rule, this is the same thing as c of 7 times negative 1 raised to the 7th power. But since negative 1 is being raised to an odd power, this alternates, and we're going to get negative 1 times c of 7. Okay? But c of 7 can also be written in the form 2n plus 1, where in this case our n is going to be 3. Okay, so this is going to be negative 1 raised to the 3rd power times c of 3. Notice that these match up. The 3 matches up with that 3. And negative 1 is again to an odd power, so this is negative 1 times negative 1 times c of 3, but again 3 can be written in the form 2n plus 1. So we get negative 1 times negative 1 times, and since this is 1, this is going to be negative 1 to the 1st power times c of 1. Okay, but c of 1 is defined to be 1, so this is just negative 1 times negative 1 times negative 1 times positive 1, which is negative 1 cubed, which is negative 1. Okay, so that is c of 15, and I will do c of 16 really quickly as well. So c of 16 is even, so that's going to be the same as just c of 2n, which is the same as just c of n. Okay, but c of n is also even, so I could write that as 2 times 4, which is the same as c of 4. But then this is again a power of 2. Okay, so any power of 2 can essentially be rewritten as c of 1, which is equal to positive 1. So I noticed that I got negative 1 on the first time around, and I got positive 1 on the second turn around. So it doesn't take much ingenuity to realize that all of the numbers that you're going to get after plugging in n equals 1 to 2013 are either going to be 1 or negative 1. So if you take the product of c of n and c of n plus 2, since you could either get positive 1 or negative 1, you can guess that you're still either going to get positive 1 or negative 1, and if you're summing a bunch of these up, I'm sure you could come up with a couple of predictions on what the final answer is going to be. So for this, I actually find it helpful to start at some random number. Let's just start at the even number 100. Okay, so we're going to let n equals 100, and we're just going to see if we can detect a pattern here. Okay, so the first one is going to be c of n times c of n plus 2. So we're going to take c of 100 times c of 100 of 2. We're going to figure out what that is. Okay, well, I already noticed something about this. I already noticed that since I started with an even number, both of your functions have even inputs. Okay, because if you take an even number and add 2, you still get an even number. And if you take an odd number and add 2, you also get an odd number. Adding 2 does not change the parity of the number. Okay, so when I take C of 100, I'm still just going to simplify that as C of 50. And if I take C of 102, I'm going to get C of 51. So I get a scenario in which these two numbers, if I start out with two even inputs, I get two numbers that differ not by 2, but now they differ by 1. Okay, and I can go on and break this up further, but I'm just going to stop here because if I let n equal 101 now, let n equal 101, that's an odd integer. So this is going to be C of 101 times C of 103, which are both even numbers, or both odd numbers, excuse me. So that could be broken up into C of 2 times n plus 1 times C of 2 times something else plus 1. Okay, well, this is going to be 50, right? 2 times 50 plus 1 is 101, which I'm sure you could guess that the next one is going to be 51. Well, that's really interesting that we got the same 50 and 51 as we did here. Can we simplify this further? Well, of course. This is going to end up being negative 1 raised to the 50th power times C of 50. So we got the C of 50 back almost for free, but it cost us negative 1 raised to some power times C of, well, okay, I should start with the negative 1, excuse me. So we have negative 1 raised to the 51 power times C of 51. So again, yes, we did get the C of 51 almost for free, but that cost us again a negative 1 to some power. But I notice that negative 1 is always going to be raised to the 50 times negative 1 to the 51st power. These numbers are only going to differ by 1, which means if negative 1 is being raised to an even power, it's going to be multiplied by negative 1 raised to an odd power. Okay, so let me just simplify this really quickly to point it out. So this times this is really going to be, well, I should probably do it in blue or something. It's really going to be negative 1 to the 50th times negative 1 to the 51st power, which is negative 1 to the 50 plus 51 power. Okay, but this is always going to alternate. One of these is going to be even and one of them is going to be odd. And if you take an even plus an odd number, okay, you can think of it as taking an odd number plus multiples of 2, which we already discovered doesn't change the parity. Okay, so this is going to be negative 1 to an odd power, which is negative 1. Okay, so what we end up getting then is we get negative 1 times C of 50 times C of 51. And you'll notice exactly that that cancels out with this in a sum, right? Because we're adding all these together. So we start with n equals 100, and if we just evaluate the sum, so if we take the sum of n equals 1 to 100 of C of n times C of n plus 2, that's going to be blah, 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 plus the 100th term. So we're going to get C of 100 times C of 102 minus C of 100 times C of 102. And that minus sign is coming from the fact that we're always going to have two numbers with opposite parities. And when you multiply those together, you're just going to get a negative 1. Okay, so what does that mean? Well, it means that these cancel. And in fact, you can make the assumption that they're always going to cancel. Okay, so you can generalize this if you want. I don't really see the need to prove this any further, right? If you wanted to say, okay, well, you know, let n equal 2k for some positive integer k. If you want to go this route, I'm sure you can come up with a good argument. But my point is the only thing that we have to be careful of is that we start on an even integer. Okay, so to finish this problem off, all we're going to do is say that the sum from n equals 1 to 2013 of C of n times C of n plus 2 is the same as C of 1 times C of 3, right? So this is the n equals 1 case. N equals 1 case. And now I'm going to start at an even integer. So the sum from n equals 2 to 2013 of C of n times C of n plus 2. Why did I break it up like this? Well, the reason I broke it up like this is because we already saw that anytime I start with an even integer, right, the next integer is going to cancel with this exactly. Okay, so we're going to have pairs of, if you want to plug this in, we're going to have C of 2 times C of 4 plus C of 3 times C of 5, and you can check for yourself that this is the same as the inverse of this, so these are going to cancel. And in fact, they're going to cancel up all the way to 2013 because this is going to be plus dot dot dot, or rather, this is going to be plus dot 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 plus C of 2012. No. Wait. Okay, so 2, 4, 3, 5. Okay, so yes, it's going to be 2012 times C of 2014 plus C of 2013, which is our last term, times C of 2015. Okay, but these are also going to cancel out. Okay, so this whole thing is 0, but we're not done yet because we still have to evaluate C of 1 and C of 3. But C of 1 is 1, and C of 3 is negative 1 to the first power times C of 1, which is negative 1. So the product of those is going to get us a whopping negative 1 plus 0 for a final answer of negative 1.